Today, we will review how to accelerate your time to market. Yes, by reviewing a mix of virtual models and real components, you can verify earlier and more often. We will discuss verification and validation in context of the V model. So this statement, yes, I guess is somewhat redundant. And we hope to show you how to avoid redundant tasks and reuse all that code and models throughout your journey. A quick agenda is as follows. First, let's discuss the V model and how that can help frame the conversation. Then, applying the need of earlier validation and verification, we can build a system. And then, of course, create a checklist so we ensure we reuse components all along the way. So what's the definition of verification and validation? Well, verification and validation are independent procedures that are used together for checking that a product, service, or system meets requirements and specifications and that it fulfills its intended purpose. This definition is from Wikipedia, so it's got to be correct. Verification, in my mind, is typically testing so that the device or system meets the design specifications, while validation is more user-oriented, testing that the device or system meets the requirements of the user's needs. Some of the various methods to verify and validate include hills, sills, and hybrid test benches. So let's set the stage. Hopefully everyone here is familiar with the V development model. Whether you are in software development, hardware development, or the entire system, this model is entirely applicable to show how each phase can influence the next, from conceptual models all the way to deployment. Typically in our world, the closer to the left side of the V, there is more simulation to prove out the concepts, while on the right side is real hardware to be validated against these requirements and the models. Of course, I can't forget that all of this is moving towards certification so you can fly. So you can pull out the various simulation and testing needs along the way, starting with 100% simulation on the left. Typically, the system or unit is simulated using a CAD tool to prove out the concept. As we get into the more detailed design, more unit testing and component testing is needed. However, some of the support signals or systems will still need to be simulated. They may still be under development or just easier to model with a simulation. Many times, this is on a single test bench. Moving back to the right side of the V, after a component is identified as a good candidate, hardware in the loop testing, or HIL, is done for integration testing. More of the other components are real, while some are also still simulated. This is done perhaps in a system integration lab, or SIL, or on a hybrid test bench. If the candidate passes the verification criteria, sometimes it will be integrated into a full fidelity simulator so a pilot can fly it. Better to test on the ground. Eventually, testing is completed on the vehicle in real-world conditions with instrumentation, of course. There is ample opportunity in this design pattern to reuse models, code, and hardware. Is this opportunity lost at your company? Let's look at some of the challenges. So first, we need to define some of the terms. I've been talking about hills, sills, and hybrid test benches. First on the list is the hardware in the loop system, or HIL. We can safely state that an embedded system is best tested with real hardware under real conditions. However, most times this is very expensive, both in time and in cost. So the next best solution is to simulate the hardware with a model and use that to exercise the system, or to test with a mix of real and simulated hardware. This can help with the test coverage, since the parameters can be easily changed in a model to a value that should never be seen with real sensors and hardware. A system integration lab, or SIL, has all the components in a system to be exercised and tested. Any that are not present can be simulated, as well as most of the signals from the sensors. I have heard the term cockpit on the ground. Many times this can include an actual fuselage so a pilot can, again, fly the system while on the ground. Hybrid test benches I have seen from our European customers. This is a mix of real and simulated components. Seems to me, at the end of the day, we should all agree on a common term. From the 20,000-foot view, all mean roughly the same thing, or at least they have very similar system characteristics. Just look at this simple system. There are all the controllers, sensors, as well as miles of cable harnesses. Why go through all this effort? Why cable up all the connectors to the controllers, to the sensors, to the simulated controllers, to the simulated sensors? Why bother simulating when you could use the real sensor and the real controller? Well, first of all, it saves money. If the controller is not complete or if it is expensive, why not simulate it? It is also easier to duplicate a simulated sensor or controller than a real one. Perhaps maybe a few were only manufactured initially on the first run. It also saves time. Many teams can work in parallel. The functionality can be verified before it is actually put on a PCB board. It also increases accuracy. You can simulate failure modes without the actual failure feedback. If the flaps fail to work in a Sill, it's okay. However, they really 100% need to work in real life. No need to put the sensor in an oven or a climate chamber. Simulation allows testing outside the normal operating conditions, even contrived or arbitrary ones. Another benefit is the regression test suite. If you have changes, run it against a suite of tests to ensure there are no unintended consequences. Someone once said, trust but verify. Some of the initial testing that can be accomplished are failure modes. The real question to ask is, can your system pinpoint the failure? Is it real? A sensor? A wire? Is it the hardware? Do you test all the extremes? The high, the low, or even the open values? How does your software react? All this is easily modeled with a simulated system or sensor. Having a method to verify the complete setup and connections helps you answer all those questions like, is this failure real? Demand it from your hardware. Your hardware should be able to determine, ensure that is implemented in your software. Through the correct selection of data acquisition and simulation I/O boards, you can easily find hardware that combine functionality to simulate and verify your systems. Analog input and output, digital input and output, major avionic protocols, CAN or AirInc 825, serial, or even customer user interface inputs and outputs can be simulated and verified. Typically, all these systems go through interconnect panels, and we have methods to handle interconnects using a computer-controlled interconnect board. The ability to switch in the real signal, the simulated signal, a fault, or even an open is invaluable for range and error checking for those faults. Or switch in multiple faults. Take control of your Hill, Sill, or your hybrid test bench. Sure, trust but verify, but don't just verify one point, which brings us to this next point. What is the difference between simulation and test? Well, in my mind, it comes down to one word, continuous. Typically, test systems only test one or more discrete points, while a simulation system in a Hill or Sill is a continuous vector type operation. Any signal or system that is simulated must provide a complete range with reasonable fidelity. Are you testing at one temperature or from -20 to 70 C? Every degree or just 3 points along the continuum? Here's a typical block diagram of a Hill, Sill, or hybrid test bench. The system integration labs, Hills, and hybrid test benches all look very similar. We have the controller or LRU on the left going through an interconnect panel. This interconnect panel is wired to real or even simulated devices, real or simulated sensors, or other controllers. Depending upon what part of the system you are verifying, the sensors could be real or simulated, or the other controllers can be real or simulated. Let's keep this diagram in mind for later. Implementing these Hills, Sills, and test benches bring their own challenges. It seems that costs are always increasing and it's taking longer and longer to realize the results. So how do we mitigate these issues? It would be great if we could share the benches and the hardware and start creating these benches much earlier in the development cycle. One thing that the COVID revolution has taught us is that remote testing and shared resources over Ethernet are not actually possible, but they actually work. We could use models or simulations for the components that are not ready to be tested yet. and the hardware can more accurately reproduce various signals, converting the virtual simulation to actual electronic signals that could be used by the unit under test. You do have a simulation of your controller, don't you? Or a simulation of the plant? All of this can be leveraged early in the verification process as well as later. Simulations are much more portable and shareable than physical hardware. We're all chasing the goal of higher availability of these test benches for more comprehensive testing at a lower cost. One solution is standardization. So why not standardize on an approach to solve these issues? The major goal being the reduction of costs by minimizing the development and validation effort of these systems. If the many vendors of the instruments or the sensors all agree on a model definition, maybe in Simulink, then it would give the users a larger choice, as well as the ability to combine them virtually to virtually try them out. With more buyers of their systems, the vendors will be incentivized to cost reduce. Also, this will show early on the interoperability between the various manufacturers. If we all get together, we can draw out the best ideas from all the different entities. Hopefully, everyone can agree on a common abstraction layer and even an API. It would enhance the compatibility with the different hardware, software, and operating systems. It even goes as far as reducing the learning curve of the various engineering teams. All the APIs would be the same. Or in a nutshell, with many vendors of instruments all agreeing on a common driver or hardware abstraction layer, all working together with the final customers and integrators, a better system can be developed. So with this in mind, I would like to introduce Vistas, or the ED247 standard. The ED247 standard is defined by EuroCai, the European organization leader in the development of worldwide recognized industry standards for aviation. This standard is also called Vistas, for Virtual Interoperable Simulation for Test of Avionics Systems. It's a good thing we can call it Vistas. Its objective is to define a common standard so that the virtual component models can be shared between the different avionic industry actors during the whole product lifecycle. For example, in full simulation, during hybrid test benches mixing real and virtual components, and even in the simulators delivered to the aircraft end user. One of the main aspects addressed by this standard is the virtualization of the analog, the discrete, and the avionic buses. This virtualization is done by digitizing and multiplexing the information on an Ethernet bus, ensuring that the timing of the signals is preserved. This last point is the key one. These lofty goals are shared by these companies who currently have team members around the ED247 working group table. They represent some of the biggest names in aerospace and aero engines around the world, with a good number of key instrumentation and data acquisition system suppliers like UEI. As we mentioned previously, that the main aspects addressed by this standard are the virtualization of the analog, the discrete, and the avionic buses. This virtualization is done by digitizing and multiplexing them onto the Ethernet bus, ensuring that the timing of the signals are preserved. We need to ensure to minimize the introduced latency by limiting the CPU, memory, and bandwidth usage so we can reproduce the original signal with high accuracy in magnitude and in timing. Why are we calling it virtualization? Well, first of all, instead of the discrete and analog signals and the wiring harnesses associated with them, it's all carried on the Ethernet line of an IT network. The data can be from real instruments or just a data packet from a model. The receiver would never know. Here's the basic transport protocol used as an Ethernet UDP packet. Don't worry, we will review this later. Looking at the high-level architecture of Vistas, everything is based on the Ethernet bus, with many different components connected to it, from virtual to real to the various tools. So let's review. Real components like real avionics, real sensors, and stuff like that, they all need an I/O bridge or hardware to convert the signals to a Vistas packet and back. This is where the actual discrete wiring happens. Virtual components generate the Vistas packets directly. These are software simulations of any component and can receive a Vistas packet to modify their behavior. And the tools, these include recorders, playback devices, display tools, air injection tools, stuff like that. Each either consumers or generators of these Vistas packets. As you see, the backbone of the Vistas packet traveling over the Ethernet network can be generated and or consumed by just about anything. The receiver does not know if it was generated by a real device or a simulated one. It's just a UDP packet. This virtualization makes it 100% usable on both sides of the V development cycle, from a full simulation on a single computer or multiple computers simulating many different devices to even full-on cloud computing. For more concrete or physical device testing, Vistas is great at unit testing where all the inputs into the system are not present and typically simulated. It is also used in integration testing with more physical and less simulation, and even in the training or flight simulator. In fact, models that generate these Vistas packets can be reused from the beginning to the end of the development chain and even into maintenance. Here's an example of a test bench that has various devices. Let's call them A, B, and C. They are interconnected by the Ethernet cable. Any signal routing is accomplished through the software configuration. All the parameters are easily displayed via the display tool. It certainly makes bench testing infrastructure much more simple and generic. And it's easy to substitute a piece of real equipment with a simulated one. After all, it's just a UDP packet writing on that Ethernet bus. Another design pattern is the replay and analysis of information gained in flight. The data is acquired and either saved directly into a Vistas format or by a converter node. The data set can be then replayed by the same display node, as well as replayed onto avionics controllers by the I/O bridge. Whether that data set was modified from the original for air injection, replayed more slowly, or as is, it's entirely up to the user. The device is just consuming Vistas packets and replaying them. Let's take this even further. In this time of a global pandemic, or the tail end of one anyway, and the fact that the various components associated with a system may be designed and manufactured all over the world, virtual testing of the system can not only save you time and money, but it will certainly help stop the spread of this virus called COVID, as well as the next one that's going to come along. The distance between the equipment is not limited by the analog wiring. Everything is over Ethernet now. The components can be in different rooms or even different buildings at the same site. They can be at different sites, or even some of it still at the OEM. This can allow earlier integration testing, earlier validation, earlier anomaly detection, and hopefully shorten your design cycle. All of this is brought to you by the virtualization of the data. So why don't we look what's on that wire? When looking at the traffic around the Ethernet bus, Vistas uses the concept of channels. Each channel is a data set sampled at the same frequency, whether analog or discrete or even a mix. Message-based buses such as CAN or ARINC 825, ARINC 429, serial, and more are also supported. For each type of channel, the structure of the data packet is defined by Vistas, as well as how the data is, quote, packetized. Each channel is associated with a communication interface, currently a UDP socket, but the standard has room for expansion, as we will see. Here's an example of the data packet, both of a single channel and multi-channel data. Mandatory fields are the actual data, with optional ones including timestamps and transport streams like UDP. So let's review. The ED247 or Vistas standard provides an ultralight way to virtualize the exchanges between real and or virtual components. It includes the capability to log and replay the exchanges between equipment with accurate timing. And it has the I/O hardware abstraction layer, making the software independent of the hardware. These capabilities allow for sharing and reuse of the models all along the different development phases. One example is the reuse of the model for the development of end-user simulators and trainers with minimal amount of work. The models also make for efficient hybrid testing where we can mix real and virtual components, easily swapping between real and virtual components on the bench. This makes the actual realization of distributed testing with the components not necessarily co-located in the same building, same site, or even the same continent. Since distributed testing is well supported, this allows for earlier integration testing, even with some of the components still located at the OEM facilities. The Ethernetization, I like that word, of the information allows for a lot of reduction in wiring and simplification. All of this equals a drastic cost reduction of the design and implementation of these benches. One part that we haven't discussed is the resolver concept of the ECIC file. This file takes into account all the components and the network information, ensuring that the data is routed to where it needs to go. It will point out the conflicts and missing sources, making for a smooth implementation. It is the key when thousands of signals are involved. The UEI I/O bridge configuration mechanism is very simple and based on two XML files. The first one is based on the ECIC format specified in that Vistas standard. It contains all the information relative to the network aspects, for instance, the IP address, port number, and the structure of the data packets. The second one is based on the pre-existing format XIDML describing the hardware configuration of that I/O bridge. These include input or output wiring, gain, filter characteristics, and stuff like that. These two files are used as arguments by the Vistas application running on the bridge. The Vistas application can then be automatically launched during boot up, making an instant on type application. So one question is latency. Well, during the past couple months, we have been doing tests to evaluate that latency and introduced by the virtualization of these packets in Vistas. We completed two of them, analog and discrete signals, and the second one on the bottom tests the Erik 429 bus. Why don't we review the top one, or the analog and discrete, first. On the left, we have a signal generator that sends a step to the acquisition bridge. The acquisition bridge acquires a signal and pushes the associated packet in the Vistas format on the Ethernet bus. The replay bridge receives this Vistas packet and generates the corresponding signal. Both these signals, the one by the generator and the one by the replay bridge, are simultaneously displayed on a scope. The delay between both can be easily measured. That was the first test. So the second one we did was this Erik 429. So looking at the bottom, we've got on the left a moving inertial sensor that sends its attitude to the acquisition bridge through an Erik channel and a message. The acquisition bridge acquires and timestamps the signal and pushes the associated packet in the Vistas format onto the Ethernet bus. The replay bridge, now we're on the far right, receives the Vistas packet and generates the corresponding Erik message. The message produced by the replay bridge is also acquired and timestamped by the acquisition bridge. This way, the latency can be calculated through the analysis of those two packets. In both cases, we measure the latency as less than 2 milliseconds. However, something like 1553 can be more difficult. Currently, the available mil standard 1553 implementation is limited to the bus monitor capability. Bus controller and remote terminal capabilities are still under development. One of the most complex scenarios we could think of to study is the one described on the slide, a configuration with a real bus controller and some remote terminals, both virtual and real, on site A, and then in a different site are other remote terminals, both real and virtual, on site B. We are in the process of finishing the communication path between both sites and evaluating the limitations based on the complex scenario displayed in this slide. The fact that mil standard 1553 requests a remote terminal response between 4 and 12 microseconds makes this scenario very challenging. Well, that brings me to my next point of a new transport candidate that we are evaluating to address these latency issues. In addition to Ethernet UDP protocol currently used, we are proposing another potential candidate, the RDMA Rocky version 2 transport protocol. The main targeted benefits of this protocol are a strong latency reduction, which could be a few microseconds on a local network, significant latency jitter reduction, really low CPU overhead, drastic packet loss reduction, the capability to offer light multicast message transfer, efficient usage of the existing network architecture, and message routing capability over a wide area network. So what is it? Well, Rocky version 2 is already largely deployed by existing IT architectures of different application domains like cloud computing, enterprise data servers, big data, and financial services, especially for the real-time high-frequency trading folks. As you can see by the slide, key IT players are involved with Rocky. So let's review the difference between Rocky or RDMA and UDP-IP. As you can see on this slide on the left, packet transfer between the two nodes with the legacy UDP protocol involves different operating system resources and multiple copies of the original data buffer. Data has to travel through the entire stack, from the application to the socket, to the protocol driver, to the NIC driver, and then onto the Ethernet board itself, and then back. That's 8 steps. With RDMA, the data buffer is directly transferred between the application and the network interface card. That minimizes the number of copies, reducing the resources needed, of course. The main targeted benefits of this protocol are the strong latency reduction. The lowest latency reachable on the Ethernet is less than 1.3 microseconds. Significant latency jitter reduction, ultra low CPU overhead, packet loss reduction, capability to offer light multicast message transfer, and as you can see by the graphs provided, throughput has increased with a marked reduction in CPU utilization. The proposed solution is based on version 2 of RDMA over Converged Ethernet, commonly called Rocky version 2. Other implementations of RDMA over Ethernet exist, like iWarp, but Rocky is the most widely deployed. It's compatible with 1, 10, 40, and 100 gigabit copper or fiber Ethernet, and also allows for link redundancy. The Rocky version 2 protocol exists on top of either the UDP IPv4 or IPv6 protocols, so it could be deployed on existing IT infrastructure and routed on a wide area network. In order to make this technology a lossless technology, it must be implemented in conjunction with those additional 802.1 standards, 802.1 QBB, 802.1 QAV, and 802.1 QAU. The new schema presented on this slide describes what could be a Rocky implementation on our new CPU board in the frame of an ED247 or Vistas deployment. This card is based on the Xilinx UltraScale Zinc chipset, which is composed of a quad-core ARM, which is a 64-bit processor running at 1.5 gigahertz, which is coupled with an onboard user-programmable Xilinx FPGA. In this configuration, we can put some of the IP down on that FPGA. The ARM cores will be involved for configuration, command, and control, and the real-time data transfer will be done without their involvement or involvement of the operating system. This system will be able to accept a very high number of packets associated with Vistas and will reduce the latency to a minimum. So why does this stuff work and how does this help you? Well, since there are no wires, the behavior or systems can be virtualized. Once a model is defined at the conceptual phase on the left of the V, it can be reused all the way to the training simulator at the end and really anywhere in the middle. It works for local testing of a component or local testing as a hybrid test bench for larger systems. Components can be added in as they are available and virtualized when they're not. And the components or even the models do not have to be co-located. Remote distributed testing works. It is currently used across Europe and in the United States. Models are being reused for validation testing and even for the flight trainers or simulators on the fully vetted and deployed products. How can this help your design process get off the ground and flying? Well, thanks for your time. I think I've used up 35 minutes, and maybe you have questions.
Thanks very much, Erik. Well, that's fascinating stuff. I've certainly learned a bit there in the last half an hour. I've got some questions, though, before we get on to anyone else's. So are there limits? As I understand it, you can have like a piece of hardware that you're testing remotely. Are there limits on the distance that piece of hardware can be from you as you're testing it?
Are there limits? Well, it all comes down to latency of the Ethernet connection. You and I are speaking. You are on one side of the Atlantic. I am on the other side. It works.
It does. It seems to be no delay at all. So is that it could go
Exactly
transatlantic? You could go pretty much anywhere in the world in theory if you've got the low enough latency.
correct. If you've got a good enough connection and a good enough Ethernet pipe, so to speak.
And that's increasingly common.
It is. It is. It's been, I said it in the presentation. One thing about COVID, what it certainly taught me is all this remote works. All of these tools work.
Yeah, we had them maybe before, but we didn't maybe trust them quite as much or hadn't tested them. Testing being the operative word. So when you're using this system, just from a high level, the idea is that you're testing the real component in this system. That's the bit that you're trying to test, right? And all the other parts are simulated to be operating at exactly as you would expect them to operate.
Correct.
Yeah.
So the whole premise is you don't necessarily need to have the complete system. If you look at typical system test or system integration labs, they are big rooms with the entire systems laid out, all the components, in order to test them. Now, what if one of the components doesn't exist? What if it's still under development? What if you don't want to have those big rooms filled full of all those wires and all those components? Then you should be able to virtualize it.
What are the challenges? Are there challenges in getting the simulated parts to work correctly? Do you have to be careful there that you're not simulating something incorrectly, as it were?
Absolutely. And that is, typically on the left side of the V curve, that is the basis of many of these systems are their simulations to ensure everything is going to work. And like any other simulation, it can be a good simulation and it can be a bad simulation. But, I think there's pretty robust ones out there. They call it digital twinning as well, creating a digital representation of your system. And the whole object is to reuse some of that IP that you've come up with all the way through.
Absolutely. We've got a few more questions coming in here. Salvatore asks, is the approach compatible with new high bandwidth aircraft avionic communication protocols such as AFDX?
We have not attempted to use this system for AFDX yet. AFDX is a high bandwidth and very deterministic bus. So we have not attempted that yet. It is on the ED247 working group's task list. I think it is going to be attacked this year. So that's an excellent question.
Something coming soon, perhaps.
Mm-hmm.
Bob Finn asks, is there a limit to how many systems and devices can be remotely tested at the same time with Vistas?
So if we're talking about how many systems and devices can be on the Vistas network in the system, there really aren't any limits. So if you were testing an entire airframe with all the different sensors for all the different systems, that can work. If Bob is talking about testing, for instance, 3 of the same controllers using Vistas, they would have to be on separate networks.
But in theory, no limit.
In theory, there's no limit other than the bandwidth, again, of the Ethernet pipe.
Right, the limiting factor.
Mm-hmm.
Stuart Langridge asks, has EtherCAT been considered as a protocol that is already widely used in industry?
EtherCAT as a protocol is more used for industrial automation and for control. It's certainly very deterministic. It's not very fast. And it would need to have some additions added in for some of the message-based buses like AirInc 429, Mill Standard 1553, serial ports, and the like. So it was not considered as a likely candidate.
but you're getting better latency presumably with your Ethernet connections using Ethernet as is.
I wouldn't say better. We are getting a low enough latency that it's certainly possible to do this.
Which actually brings me on to, I was interested at the end there. You were talking about the Rocky version 2 system, low latency being one of the real benefits of that. And is that's the way it's all going? Is there a time when you don't need that and you can rely on the previous system, or is the higher latency always going to be a benefit?
You mean lower latency is always a benefit for
lower latency. I mean, yes. Higher speed, lower latency. That's
higher speed and lower latency. Yes. Yeah. So I mean, again, speed and latency. Our internet connection here is good. You and I, our video shows up the same time as our voice. If there was latency, then you might see me freeze and the voice continues because there's less bandwidth. You still need the speed to move all this information across. Will there be a time with the infrastructure where latencies will be low enough? Well, the whole Ethernet backbone will need to be reconfigured, reorganized, and re-architected for that to happen. And I don't know. I really don't know if that's on the on the horizon for the next 10 years. We shall see.
No, but the Rocky 2 is that's the best. That's the sort of gold standard right now, as you know, using the existing infrastructure.
Yeah, so far, and yes, you would need a specialized Ethernet card in your machines in order to accomplish this. And again, where we learned about it is in the high-speed trading of these traders. You don't want a bank in London fighting with a bank in Boston over, if they're in the same organization to trade. And so they use these links and it works. Every penny counts, apparently.
Absolutely.
Absolutely.
Yeah, that's excellent. And sort of from a very high level, where does the sort of simulation and the whole thing that we've been talking about now, where does that end and you have to actually go into the real world and test in the real world? Where do you draw the line? Is there a risk you end up simulating too much? Is
there a risk? Well, if it doesn't work in the real world, if your simulations aren't correct, yes, that is the risk. But the whole idea is if you are creating an airplane or an airframe with a controller and you want to crash it on the ground, you don't want to crash it in the air. So there are simulators. People have full-on simulators where a pilot flies that new controller on the ground to ensure everything is going to work. Only after that do they take it in the air. And then in order to pass FAA regulations here in the US, yes, it needs to have documented testing proof in the air as well for certification. Definitely.
This whole system will basically speed up the process. That's the main thing.
Yeah, the main thing is to do more parallel testing. So, if my sensor is still under development for your controller, you can start testing your controller without waiting for my sensor or vice versa. Certainly. Or, there's more than one computer in any system that we have these days, and they're done by different vendors. So they've all got to be tested together as a system. Testing in parallel hopefully catches some of the anomalies earlier in the process so they can be fixed and not later. The earlier in the process you can catch them, the less expensively you can fix them.
Fantastic. Well, I think that's a good point to sort of wrap things up. There's one other question, which was from Timothy Chow, Tim Chow, asking if the presentation and slides will be available. But I can tell you that yes, the whole presentation will be available on demand, pretty much just within an hour or two of us finishing here. You'll be able to get this on demand. The slides, if you look at your screen right now, there is Erik's email address, and I think I'm right in saying, Erik, you're happy to take emails with the request for slides.
Absolutely.
So yeah, drop Erik a line. One last question before we wrap up. Are there any products tested by this system already deployed in the air? how does it compare to actual performance of the system in real time?
The answer to the first question is yes, absolutely. Airbus is a big proponent of this and is using it across their systems. How does it compare to actual performance of the system in real time? I believe we would need to talk to some of the manufacturers to find that out. Again, it seems they have studies showing that it decreases their time to market, decreases their cost on various components that they are using in their systems.
Oh, great. And again, perhaps something that people may like to email you about and find out more. The conversation will continue. We'll continue to follow this technology in the magazine, on the website, across our channels. So stay tuned to Aerospace Testing International as well. And we'll all keep in contact and keep this conversation going. So thank you so much, Erik, for your time.
Thank everybody as well for their valuable time.
Absolutely. Thank you, everyone, for being here. And as I say, do feel free to share the on-demand links with your colleagues for future reference.